Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Now, the next one we're going to have a look at here is we have 4 sunflowers, A, B, C and D. And they've start heights of 3, 6, 6 and 8. Okay, so what we're going to look at here, is there a pattern to the growth of these sunflowers? Well, first of all, you walk into a shop and you're trying to buy sunflowers to grow in school. Which ones are you going to buy? You'll walk into the shop and what are you going to see? What's the whole idea behind sunflowers? The fact that they grow to lovely heights. So you walk into Woody's and what do you see? Product placement there by Woody's. What do you see? The tallest one, and you go, I'm buying those ones. Then you go over and you read the fine print. Then you do a bit of reading and you go, well, hold on now. How could we try and work out which is better? Do our chart, our graph, or our table? Is everybody happy with that? And that's what we're going to do, okay? Now, so what we're going to look at now, look at the time is 0 because remember what we said. Why is the time 0? As soon as you walk into Woody's, what's in front of you? A plant of a certain height. Does that make sense? So it has initial height there at the start. And then what you're going to look at is, you're going to look at filling in the table. Once you have your 2 tables done in, you put the 2 plants on the same graph. What's particular about A and B that you can pick out very easily from the graphs?
They're growing at the same rate.
Because they're parallel. Would everyone be happy with that? Now, moving on to the next one, B and C. We have them in green and red here. The C must be growing more than B all the time. Why? Because why? It's clearly, you can see that it's always going to be ahead of it. Is everybody at that? So what did they had? They had the same starting value. Now, we have to be careful because look what happened there. They had different starting values, so I put one ahead. What about these ones? They had the same starting value, but what about them? It was the growth rate that put these ones ahead. Is everybody happy with that? Okay. And our third one then. Who's ahead here? The green or the red? C or D?
C.
Exactly. Can you see that? It started less, but it had a greater growth rate. We definitely have what? On day 2, they were the same height of 12 centimetres. Does that make sense? On day 2, they were the same height of 12 centimetres. Okay? And that's on a graph what we call a point of intersection. So this one leads us to what? First of all, it looked like what? The first one looked like what was the lad that put you ahead? Your initial value. Second one, it looked like what? The growth rate put this one ahead. And thirdly, actually a mixture of both. So let's try and answer the questions then, based on your different graphs. We all have the same questions, but let's have a look. What values are varying, folks? The height, and something else that we tend to forget. Time naturally varies. Now, does one depend on the other? Yes. In what way? As time goes on, what are you hoping is happening in your plant? That your plant is getting taller. Because why? As your days increase, your plant gets taller. Now, identify the rate of change of growth with time in the table. The rate of change of growth with time. So where's this in the table, folks?
It's the difference between...
Exactly. Look. 3 to 5, 5 to 7, 7 to 9. Is everybody happy with that? Okay, so there are your growths. Now, where do we see this in the graph? It says the growth with time.
Change per day.
Change per day.
So if we look, what's happening here? For every day, grows by 2. Okay, what values are staying the same, folks? The growth rate is staying the same. It's no matter where I draw that triangle, it's always the same. Now, so we're going to now move to getting this into a formula. Describe in words the height of the sunflower A on any day. Well, what will we do here? We know this now from our what? From our last question, right? So what are we going to use? Well, let's go with H for height. And what other letter will we use? D for day. Why do I not need R for rate? Because what's the rate of growth? For plant A, it's 2 centimetres per day, isn't that correct? What was its height at the start? 3 centimetres at the start. So what we should be able to do is we should be able to put all of this into an expression. How will we put all of this into an expression? Well, even look at this here. 2 centimetres per day. What's that telling you?
D multiplied by 2. 2D, yeah.
And then, why are you adding on plus 3 to them? Because it gets what it had at the start. And then what will we just say? Well, won't that be what the height is? Is everybody happy with that? Okay, so that's what we get there. Now, identify the variables and the constants in this formula. Well, what do we say it's varying? The height of the flower is varying with respect to what? To the day of the week. And what do you notice? The height and the day are the ones that are letters, which are variables, the things that are varying. What are not varying? The starting value our starting value and our rate are not. And what do you notice about them? They are numbers, they're constant, they're never going to change, okay? Now, where do the y-intercept and the slope of the graph appear in the formula? So if I point to this one.
The Y is the start.
So that's your start when you're looking at it in a table, and it's also what? Your y-intercept. And like we said here, what about this too? It's your growth, and this is your slope. Is everybody happy with that? Okay, now, so that's just putting in all the things. And what do you notice about them all? They all start with 3, and what do you keep doing? Adding on 2's. Now, so what multi-representations did we look at there? There was a table that we got a certain amount of information from. There was a graph. There was words, which we were able to convert into symbols. Where does something like a table maybe fall down for us? Supposing I asked you to do the 25th one. Do you reckon you'd be bothered going doing a table? Where might you prefer to go to? Yeah. Go to your formula, okay? And supposing then I just said the 10th one and you didn't want to use your table. Where might you easily be able to get it from? Your graph. Go up to your graph and draw your line. What can be a problem with that, with a graph? You go to day 10 maybe and you go up and you hit the line. What could have happened? And the same even with this. The plant at that stage may not have been growing at the same rate or whatever, but you have to just take all the ones into consideration at that particular time. Is everybody happy with that? Okay. So the idea is don't just take a range of values and assume that it works all the time. Okay. Now, little question for you. Draw a rough sketch of this graph. What knowledge are we working on with our students? We know that this is a what? Now, it's our y-intercept, it's our starting value. And when we go to our graph, that's our y-intercept. What are we talking about here? This is our growth. And whether they know their slope or not at this stage, they at least know what? It's what's making it build. Is everybody happy with that? So basically, a very rough one of this is trying to do what with them? Mark off a 1, and then what are you saying to them? What does this 2 tell them? For every increase of 1, the graph grows by 2. So over 1, up 2. Over 1 and up 2. Is everybody? And then up goes their line. What can you also do? What did you do out, Stephen? Stephen did out his table. And after getting a few of them, hey presto, away we go. Okay, are you happy with that? Okay. Because at that stage, what have they not gone? Let x equal 0, let y equal 0. They're not at that stage yet. And that's your graph, because why? They're spotting their steps of stairs. How about this one? Same idea, but you're just giving it in sentence form. Now, it's even easier when it's given in English like that, because why? It's actually telling you the parts of your graph already, because what's it saying to you? Starting off at 6. So basically we definitely know what? Starting off at 6. Now how did I get my growth rate in? Well, €3 each day, so that meant what? Over 1 and up 3. Over 1 and up 3. Okay? And the last one for you. Right, well, is that speed equals 10 plus 2 times the number of seconds? Everybody happy with that? So, now why did v is equal to 10 plus 2t, or v is equal to 2t plus 10, whatever way you want to look at it. How will that transpire onto the graph? You're starting 10, and then, now, here's a nice interesting one that I just put up on my one. It might not necessarily be the case on yours. Remember, what did we say? Over 1 and up 2. Over 1 and up 2. What does it look like mine is doing? Over 1 and up 1. But am I counting boxes? No, I'm counting what the actual box stands for. So when you look here, over 1 and up 2, what am I actually, well, it's over 1 and up 1, but what about this? That 1 is from 12 to 14, so it represents 2. So you're getting into the harder ones then with them at that stage. But they've an awful lot better feel now for what? The idea of what the slope is and the rate of change. And then finally, something then which just is nice to show them about the different slopes. Okay, what do you notice about all these ones?
They're greater than 1.
Exactly, and all these lads? Less than 1. And something as well which is very unusual for students at this age. What about them? Where do you reckon they expect the slope of 2 to be? Halfway between 1 and 3. Does that make sense? So it's a nice idea to just get the concept and see it once to go, well, no, we'll be coming across that when we get to our trigonometry. Okay? Okay, but it's a nice idea for them to see that, look at that, it doesn't span itself out nicely in the way that we would expect it to. Now, all the graphs you have drawn on your whiteboards have been increasing functions. Isabel had a money box with €20 in it, and she starts to take €2 out every day to buy sweets in the shop. What will she draw? Or how will we draw it? Just do a quick sketch. Okay, So you'll get something like this going on. Everybody happy with that? Yeah. Okay, and what about your ladder this time? Every day it's going across and down instead. Is everybody happy with that? Yeah. Okay. And then, you know, if we were to do out a table, where will it turn up, folks? Let's go back and see. It says from your table, what is the rate of change? Well, where would we see it? Well, let's have a go. We go with day 0. So we have time and we put amount. So on day 0, what did she have? 20. Day 1, day 2, and 3. Okay, and now, important for them then, like I have done on the other ones, to get the students used to is what? Yeah, the change, not to put the number 2, because why? It's -2, because remember, it's decreasing, and you're trying to get them into a negative rate of change, which means a decrease. And what about that slope? That slope as well, we'll be referring to it as negative when we get to that stage when we're in our coordinate geometry. So it's important that they don't look at the change, it's just plus or minus, or sorry, the number on its own. They need a plus and a minus. Now, the next thing that I just want to show you is the connections that we've brought together throughout this. You started off with your unifix cubes, which led you into what? Simple pattern predictions, simply from having a look, which then sidelined to what? Starting values, variables, and rate of change, or rate of increase at that time. Okay? The next thing we looked at then was y equals mx plus c is where that was leading you to do. Where can you spin off from that then? Concept of slope as a rate of change. Okay? And it's then led on to where the point of intersection. Now, where can the learning then be moved from this? The next thing we look at is growing squares and rectangles with you. Now, from a sideline point of view, what are you starting very early with them? Periodic functions. It was something they never hit in school until they actually got to 5th year and they found the concept. If they're talking with trigonometric functions, periodic functions tends to be quite difficult for them. Okay, multi-representational approaches. So they're looking from tables and graphs, which one is best for better situations. And also, what have they got? Independent and dependent variables and covariational reasoning. Now, what does covariational, it sounds very specific, but basically 2 things changing at the one time. Does that make sense? At the same time. So if your x's and your y's, or the days of the week and the height of the plant and so forth and etc. Integration. Integrate under a line, making the diagram the volume of revolution of a cone. So that's right up at the very top end. Okay, coordinate geometry. When they get to their coordinate geometry now, what about it? They should have a far better understanding of their slope, points of intersection, things like that. So you should be only doing what when you get to the line? You should be only consolidating the fact that, look, this is a formula now that we can use on the coordinate plane, but they should know what slope is. Okay, concept of the slope as a rate of change. Well, what have we looked at now? If something is linear, what did we notice? It had a constant rate of change. Next, in coordinate geometry, you have your slope formula, and trigonometry there, as Stephen was saying, you can do the relationship between what? Your slope and your tan. Because remember, what are you looking at there with them? If we were looking at a very simple line like that, what did we say? Over, for every day it grew by such an amount. So if we angle that off, what will that become? The opposite, and that will be the adjacent. So obviously that is your tan, which has something to do with the connection to the slope as well. Okay. The point of intersection. Okay, what does it mean from a problem solving? If I told you that it was 212 for that point of intersection on the growth of the plant, what does that mean in everyday language for the growth of the plants? 212.
They're both 12 centimeters.
Exactly. On the second day, they're both 12 centimeters. So do you know what those points actually mean? Okay. And then algebra, well then you're into simultaneous equations and your point of intersection. And then your growing squares, which we're looking at next, brings us right into sequences and series. Okay, so we'll have a look at this growing squares. Okay, so we have a pattern there. So what do you see? Many red squares? And many white? Okay, so let me give you the second one. Do you reckon you know what the third one is? Have an image in your head, please, of what you think the third one is. Was that what you were expecting? Is everybody happy with that, yeah? And then, obviously, with your students, you might get them to do what with it initially. Draw these out, but we won't make you do that here today. And everyone, an image in your head of the fourth one? Okay, and an image in your head of the fifth one. Now what I'm going to get you to do is, very roughly, okay, I'm just going to ask you to come up with a formula between the whites and the reds. And that's all I'm going to say. What strategies have you available to you folks? What do you know already? Tables? Anything else that helps you out? First of all, what do you see in front of you?
A pattern.
You definitely see a pattern. So you see, visually, you knew what was coming next. What do you want after that, though? What was our next thing? Once you see your pattern, what are you trying to observe? Yeah, what's happening? What's coming next? Is everybody happy with that? So at the end, we'll have some equation written down. Okay. So if you have, well, what do we know? If we have one white, it will mean it'll be 8 reds and so forth. So we'll have some equation going around. Jada, with your one, what was your thinking?
Well, there was 6 reds in every single pattern.
Where?
In the ends.
Right.
So, and then that there was for every one white, then there was 2 reds. So I went 2W plus 6.
Exactly, and Michael did the exact same logic thing, no table routing, straight into, well look at, what can you see? The 6 is actually remaining constant. Does that make sense? Now, there was other people then who went for the table, so Deirdre, I'm going to look at your table. What did you get? 1 and?
8, 10, 12, 14.
Okay, now, and I saw this on the girls, so now, the change is plus 2. Is everybody happy with that? The change is plus 2. So that means, what did you get in your formula then?
I had R equals 8 plus 2, 5W minus 1.
Okay. Now, and let's have a look at this. Are you happy enough with that? Well, why? We definitely are using 2 here by the what? The number of whites, which is definitely correct. If we simplify this out, what does it become?
8 plus 2W.
8 plus 2W minus 2, which is still what? 6 plus 2W. Is everybody happy with that? So it actually is the exact same thing as was seen visually. Now, so what the characteristics now do we know about a linear relationship? The first change is constant. Now, what was it in our example here for this table? Our first change is?
Plus 2.
Plus 2. It had an n term. There was only n's or w's or so forth. There was no squares or anything. And it was a linear graph. Okay. Now our next problem for you to have a look at. Complete the next 2 rectangles in the above pattern. Now, is there's squared paper in your handbooks? Now, we needn't worry about this, but we would have our students doing it. The colours mean nothing here. The colours are simply to help you out. Anyone tell me what the next one will look like?
It's 2, 4, 6, 8. Yeah, so it's 5 by 4.
5 by 4. Why 5 by 4, John?
Because you're increasing the length by 1 and you're increasing the
Height.
height by 1.
Exactly. Is everybody happy with that? Yeah? Okay. Now, what we're going to do is, I wanted to do up a table with heights, lengths, and area. Okay, so just do up 3 columns, height, length, and area. Okay, Michael, will you give me a dig out here?
1, 2, 3.
122, sorry. 236. 3, 4, 12. 4, 5.
And 4, 5, and 20. That should be loads from the time being anyway. Is everybody happy enough with that? Okay, so let's have a look at it. Is it linear from your table? Remember what we learned? We're going to look here at, let's have a look at the area. We're going to have a look at this area. Plus 4. Now, next one, Harry.
Plus 6. Plus 8.
Plus 8. Well, is it linear?
No,
Why?
because the rate is changing up.
Exactly. That rate is changing all the time. If that was linear, we would have the same change. So definitely it's not linear. Do you notice something about those numbers?
They themselves.
They themselves are linear.
Well, 4, 6, 8.
How are they linear?
It's gone up in 2.
Right.
The rate of the rate is gone.
Exactly. The rate of the rate, or if we call that the first change, what are we saying about this? This is the second change. Is everybody happy with that? And we'll even do one more line. 5, 6, and what, Michael? 30. And then what will Harry put in? Plus 10. And then back to you, Michael, what will you put in? Plus 2. Now, so we definitely know that it's not what? It's not linear, okay? But what about it? The second change is linear, or the second change is constant, which leads it to a different type of function, okay, because it's not linear. So here we have our table, so we have our changes done out. Okay. Now, let's see, can we write a formula for it, folks? Okay, so remember, what are we going to have? We're going to have that our area, or I suppose, if I call this n for the height, what will I call this one? N plus 1. And then obviously what will I call the area? N times n plus 1. Is everybody happy with that? Okay. Or at the start you might have h and h plus 1. And then kind of h is not a good one, why? Because it particularly stands for the height. But here we wanted to stand for height and length at the same time. And if to go back and look at the picture, that is clear as well, because why? 1, 2, 2, 3, 3, 4, n plus 1, n plus 1. Does that make sense? So it is clear from the picture. Now, what does this give us? When we multiply it out, so obviously this is not linear, so we're into our what? Quadratics. And obviously what would you have your students do then? You'd have your students draw it to what? To see that what it actually does look like. Because remember at this stage you don't know what it actually looks like. And then they will come up with this. What about it? Well, the first change varied. Where did we get that? Well, isn't that what Harry gave us when we filled in our table? Okay, then second change constant. Isn't that what Michael gave us? Okay. We've n squared terms, or if you had h, it would be h squared. It needs some squared term. And then once your graph would have been drawn, what would you have got? That it was curved. Okay, so that's what would lead them into a quadratic relationship. Now we're just going to look at one more relationship very quickly and then we'll take our lunch. Okay, so how to ask for pocket money. Okay, I only want to give you pocket money for the month of July. All I want is to give you 2 cents on the first day of the month, double that for the second day, and double it again on the third day, and so on. So on the first day you get 2 cents, the second day 4, and on the third day 8, and so on until the end of the month. That's all I want. So if you went home from school someday and asked for that, what do you reckon? Would the parents be impressed? They shouldn't be. Why, Stephen?
Because the rate of change is what you want to double it each time, so by the time you get to day 31, it's going to be quite an amount.
Exactly, okay? But when you ask that to people, or if you said it to probably majority of parents with, you know, that maybe their maths background is in school, what are they going to say? No problem. And where do we say no problem to it? When you go in and sign your name on the dotted line for your mortgage over 35 years, and we still say no problem. Okay? Does that make sense? But it's the same idea. What keeps happening? Everything is compounding. So let's have an analysis of this. Would everyone agree like this? We'd analyse it using a table. Okay? Now, so what do we get then? Can we write a formula for it? What would we write? 2 to the power of the day. Is everybody happy with that? 2 to the power of the day. Okay? And then next thing then, our formula is 2 to the power of the day as we have there, and we call it doubling. Now on our junior cert day, we'll have to look at doubling and trebling. Now the idea is, obviously what kind of functions are they? They're exponential functions, but they're not going into that level of detail. But they have to know that as opposed to what? If they look at linear or quadratic, they do grow. But what about this one, this exponential? This really does grow. That's the idea you're trying to get across to them, that the doubling and trebling in an exponential is absolutely huge. Okay? So, if we look there, there's our graph of what it looks like. And what do you notice about a trebling one? Now, because remember, they're only going to be looking at doubling and trebling.
It reaches the same point quicker.
Exactly. What do you notice? It's growing, but it just is growing far quicker for trebling. Is everybody happy with that? It's growing far quicker for trebling. Okay? So that's what they have to realise, the difference between them in terms of their growth factors and doubling and trebling. They're not going to be coming up with formulas or anything at that stage. Okay? So let's look at the changes. Well, what are you expecting? So what's our change in the first one, folks? Now, go again. What have you knocked out by this one? What's it definitely not? What kind of... it's definitely not linear. What have you knocked out here? Go again. 2 to 4. 2. 4 to 8. 4. Okay. What's it definitely not? Linear, quadratic. What comes next? Cubic. It's certainly even not cubic. Okay. What's going to keep happening this? It's going to keep generating itself over and over and over again. So what happens is they develop in a ratio. When you take any one divided by the one before it, what happens? You will come out with the ratio, which in here it's obviously what? The number 2. If it was a trebling one, it'd be the 3. And can you see where it's going then and leading into their differentiation? What type of functions is it leading them towards? They're exponential functions, and what happens when you differentiate them? The function is always back in the answer. Because why? You never actually get rid of that part of it. If you think about differentiating e to the x, what happens? E to the x, differentiate it again, e to the x. So it just keeps remaining the same, okay? So there's a nice logic going on to their calculus with the rates of change, okay? So what do we need to know here? A change develops in a ratio. The formula is 2 to the n or 3 to the n, and the words for this is doubling or trebling. Now, like the one for quadratics, it was a curve back, but what are we saying about this one? It grows very, very, very quickly, okay? And these are the characteristics of an exponential relationship. You're not going into E or anything like that, okay? And then, if you just had something from your own point of view, if you look at that formula there, and I've calculated out the interest rates for, I set all the variables equal to 1. So yearly, semi-annual, quarterly, that's all is changing. What do you notice when you get your interest rate every second? What number is that? E. Your E, which naturally occurs everywhere, and unfortunately is there sticking in with your good old mortgage, which is, or whatever it is, building up every second. And it's very hard for students of that age to realise, if you even ask them to do 2 to the power of 10, they really think because that 10 is quite a small number, that what? You're still dealing with quite small numbers. It's very hard to get that multiplying idea across to them. Okay, so that's our morning part over.